All right, picking up where we left off on Friday. Remember, we've started talking about electrolytes and non-electrolytes. And what is an electrolyte? Okay. What does it do? It conducts electric current. The reason it conducts electric current is because it has what in solution? Ions. It has mobile charged particles. Okay. So that's an electrolyte. A non-electrolyte is essentially the opposite. It does not conduct current. It has no charged particles in the solution. Okay. Now, there are two types of electrolytes. What are the two types of electrolytes? Strong and weak. There is one number that is associated between both of them. How do you define strong? What? Okay, dissociation, soluble, ionization, all three of those words work. Okay? Now, that is what strong means. Anything less than 100 is considered weak. Now, so if it's 99, it's weak. But I said most of them are less than what? 5. Okay, just kind of go along with that. So ions tend to stay in solution where they can conduct a current rather than reforming as a solid. That is a very interesting question. Or not a question, a statement. So what you're basically saying there is that instead of them actually floating around and saying, hey, I'm a positive thing, there's a negative thing, let's make an attraction and reform the solid. They actually don't prefer that. They actually prefer staying as a conductive current. A conductive solution. So they prefer having that electrolyte. They like being mobile. They like being able to be free reign. Right? Do you guys like changing classes versus sitting in the exact same class all day long? Okay. You would get old you'd get old sitting in here all day long. Okay. 48 minutes. I mean, even when I was on block, 90 minutes was about your peak that you could actually sit in the same room once you get this age, okay? So this is kind of the same concept. Instead of having to sit and stay stationary in the same place all day long, they like to be charged, they like to be mobile, and like to socialize, okay? The reason for this is the polar nature of the water molecule. Now, we've talked about water. Remember we called it I misspelled that again, didn't I? There's only one R. So we call it the piranha. So the way that the hydration forces work is that it engulfs these particles and allows them to stay as the charged particles. We already know this, and I'm telling you, when you have to draw this stuff, it's definitely going to come into play. The positive ions. Now, there's another word we can say here. Positive ions are known as what? Cations. The cations are associated with the negative end of the water dipole. Now, this is a funny word that we've never seen before. We've kind of seen it, but I want to kind of get your concrete back into it. What is a dipole? Two poles. What are the poles? Now, this is an important question. These poles, these water molecule poles, are they fully charged or partially charged? Very good. So let's make this little symbol here. So remember, we've got the partial positive and the partial negative. That's what a dipole is. So a water molecule is a dipole. Does that make sense? Now, can you stick a water and a water together? Yes. Hypothetically, what type of intermolecular force could that be? A dipole-dipole. That's where that comes from. So if you have a dipole A and dipole B, can you make a dipole-dipole between them? Yes. Now, water does not have defined dipole-dipole. They have a what? Hydrogen bond. The only thing that makes a hydrogen bond special is that it's a little bit stronger than a dipole-dipole. Same concept, but it has to have a hydrogen and what other elements? Followed. Okay, so making sure we're on the same page there. Now, okay. Yep. So let me, just in case we're here, okay? Bonds. And again, I know that some of you need to see this, so I'm just going to do it anyways. Actually, I don't like that. Right. Now, my first question to you is, what is a bond? Okay, this is between atoms. Does that make sense? Okay, an intermolecular force is what? Okay. Between molecules. Between Sorry, between. Wow, that did get a little ugly right there, didn't it? Sorry, I didn't mean to talk about you, Ryan. All right. Now, I promise I'll come right back to this. So if you're not finished with it, I'm going to come back to it. So when we talk about um, so my question to you is, what is a bond represented by? Okay, this and those. These are bonds. Based on what you just wrote, how do you know that those are bonds? They're between atoms. Okay? What is the IMF represented by? Dots. Now, I'm going to go ahead and tell you, I kind of cheated here. A hydrogen bond is represented by 3 parallel dots. Okay? Yes, in a line. Okay. Now, hydrogen bonds are represented by 3 dots. Other IMFs are not. Okay, but I cheated there because I do know that this is a hydrogen bond. If you ever go back, and I can show you a picture of it, if you ever look at DNA, remember that you have the nucleotides and the base pairs, how they match up? If you'll ever go back and look at one of those drawings, between each adenine and thymine or guanine and cytosine, there should be, if it's drawn correctly represented, there should be 3 dots between those letters. And what that dot represents is a hydrogen bond. Okay? The reason that those things are held together with hydrogen bonds is, does your DNA nucleotides, do those things need to separate from each other at any point? During what process? Replication. Okay, DNA replication, right? The helicase comes in, your DNA splits, it creates an identical copy of itself. Yes? Okay with that? Okay. So, you've never probably known that, but what holds your DNA together, those base pairs, is a hydrogen bond. The way that the molecules are set up are hydrogen bonds. And I'm not getting into the depths of it. Okay? Yes. Okay? So, this is kind of what I want to go back to. Bonds. Of the two, of the bonds versus IMFs, which one is stronger? Bonds are stronger. Okay? The way we know that bonds are stronger is you can compare BPs, you can compare MPs, and you can compare, there's something else. Thank you, I apologize. Boiling point, melting point. Okay. And there's something else you can compare. Actually, you know what? I erased that. That's wrong. My apologies. That is wrong. That's on the intermolecular force side. And let me tell you why that's true. If you boil or melt water, is it still water? Is that a physical or chemical change? Physical change. When you have a physical change, are bonds broken? No. That's separation of intermolecular forces. Does that make sense? Okay, my apologies. I wanted to make sure. So there are 3 types of bonds. The 3 types of bonds are ionic, covalent, and metallic. Now, I know I'm spending time on doing this, but I feel like mentally it's good for you to see it again. Okay? Now, just real quick, what things make up ionic bonding? Ions. And electrons do what? They're literally transferred back and forth. Now, I lied to you a little bit last year. Okay? I need you to understand this concept. And I promise I'll come back to the screen. When you've got Na, and it's got 1 valence electron, true or false? How do you know? It's in group 1. And you've got chlorine, and it's sitting over here with 7 valence electrons, true or false? How do you know that? It's in group 17. Here's what I need you to understand. Does this sodium literally give its electron to hydrogen and say, deuces, I'm out? No. Okay? It stays put. It doesn't go anywhere. So when we say the electron is transferred, it is given away. Is it literally said here and just dips out? No. It's what this is. In a weird, strange way, you know how I draw the loop-de-loops? It's literally like this. There are no loops on the other side. But there has to be some sort of attractive force to keep it as a crystal. Okay? Yes, it's the positive and negative part of it. Yes, and so what he just said is actually true. This turns very positive, right? This turns very negative, so it sucks it back in a very weird, strange, elementary way. Okay? So it is still there. They're technically kind of shared, but you're looking at less than 1% that electron ever goes back. Okay? So that's why we say they're given away, but they're really not. They're still attracted to each other. Okay? Now, in a covalent bond, we know electrons are shared back and forth equally or unequally, right? There's two different types. What type is it when they're shared equally back and forth? Non-polar. Yes, sir. The fact that electrons technically aren't given away. They're really shared, but very limited sharing goes on. Okay. And then finally, the metallic, and if you want to write this underneath here, I'm too lazy to bend over and write it, so I'm going to write it up here. Metallic has a special thing. Do anybody remember that special thing? Very good. It's a sea of electrons. You can write that underneath metallic. But what that means is that the electrons literally do not belong to any one atom. They are free to roam and go wherever they want to go. That's exactly why it conducts electricity. Okay? And I want you to think about this, and this is getting the depths of what we didn't get into last year. What happens to electrons when the energy and the thermal capacity, and when I say thermal, what do I mean thermal? Heat. When heat is applied, what happens to the electrons? Okay, they speed up. They move faster and faster and faster. Okay, so the metals that conduct heat really well, what does that tell you about the velocity of their electrons? They're a lot faster. So that is really why some metals get hotter than others. It's because their electrons are more mobile than others. Never thought about it that way, but that's what it is, sir. That's exactly what it is. It's the kinetic energy within the particles. I know you got a question. Go ahead. It's just the movement of electrons. Yeah. I mean, there's a, and it's funny you were talking about Twitter earlier. There is a Twitter page that I forget what it's called. It's something that's like destroy stuff or destroy something. And there's two different things they do. They put random objects. They did donuts. They did an eraser. They did all kind of crazy stuff under a hydraulic press. Okay. There's another one where they take nickel like spheres. They're like real. They're just like round nickel spheres, and they heat them super, 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 super high, and they just drop them on random stuff. Like they dropped it through cotton candy the other day. They put one on a jawbreaker, and like they show you how like it melts and stuff. But nickel has a very high heating capacity, which means it can absorb a whole lot of heat, and the temperature can go up without destroying the metal. Does that make sense? Like the metal doesn't melt. It still stays solid, but the energy stays within the nickel. I haven't seen that one. It turns back into wood. Now I've seen them do a book, but like it just shot out of the sides of it. Now the one that I may get to it if we ever have time one day. The thing that grossed me out the most, they did two things. They took a McDonald's Big Mac. They pulled sulfuric acid on it. Nothing. They took molten copper and it rolls off of it. Like they poured it on the bun and it rolled off, and then they opened up the bun and poured it on the patty and it rolled off the patty. Molten copper on a Big Mac. I'm dead serious. If I get time at the end, we'll go to it. Okay? All right. So, back over to IMFs. Now, these are between molecules. There are three. There's the LDF. Now, LDF stands for London Dispersion Forces. Now, here's what you need to know. Okay? This is between two non-polar molecules. Now, here's what I mean by that. Yes. Here's what I mean by that, and I'll demonstrate it. Let's pretend that we've got F bonded with F. We've got another F bonded with F. Now, first of all, how many total molecules are present? 2. Okay. Which element in either molecule is more electronegative? Neither one of them. They're the exact same electronegativity. True? So here's what's going to happen. Your electrons are going to be shared equally. True or false? True. So in essence, should you have partial poles in either one of these two things? No, but here's the concept. How many total valence electrons do we have with both Fs? 14 each, because they each have 7, right? Okay, so here's the deal. Since they each have 14, is it always 100% of the time going to be 7 on 7 and 7 on 7? No, because what are those electrons doing? They're out there running around 100 miles an hour. Actually, they're moving at the speed of light. So, in a moment, and they call this a dipole moment, for a split amount of time, okay, nanoseconds, milliseconds, whatever you want to talk about, it is possible for you to get a 1 versus a 13. And it is possible for you to get a 2 versus a 12. If this momentary thing happens, can partial charges be created? Yes. And in this case, would you agree that you have a partial negative here and a partial positive here? If that's the case, what then can then be created between those two things? An IMF, an intermolecular force. The way that I like to think about IMFs, not an IMF. An IMF can be formed, but which specific type? This is an LDF specifically. And the way that I like to think about an LDF is kind of like a high five. For that momentary split second, are you connected? But you let go and you kind of keep rolling on. Okay, that's how I like to think about LDFs. Is that they're very quick, they're very short, and they happen because of disproportionate charges because electrons are constantly moving. Okay, now the other two, we know we've got a DD, which is dipole-dipole, and then we've got a hydrogen bond, which I hate that name. The reason I hate that name is because it's very misconceiving. Are hydrogen bonds bonds? No, they're forces. I personally wish they had changed them to something else. Okay. By the way, I do want to say this. If you ever see the word van der Waals forces, that's the exact same thing as an LDF. Okay. Fritz London and somebody van der Waals were the two guys that worked on it together. So you hear them kind of like torr in millimeters of mercury. They mean the same thing. It's just two different names. Okay. So dipole, two polar, hydrogen bond, two polar, but you must have H and Fon. Now, I read the article to you last year. They actually found a molecule with hydrogen and phosphorus that actually created a hydrogen bond. Fonop. Look at you. Sir. The differences in the electronegativities. Yep. And there is a range. The problem that I have always had, and honestly, I figured I did it in college, I've done it in high school, and I've done it as teaching. I struggle with knowing which chart to use because there's two different charts. You can look in one book, it gives you different ranges than another book does. Okay, so what they're basically saying is if you take F and H and you subtract their electronegativity values, depending upon what chart you're looking at, fluorine is sometimes 4.0, or I've also seen it as like 3.98. And most of the charts we look at for hydrogen are 2.1. Now, if you subtract those, what do you come up with? 1.9. So here's what I've seen. I have seen scales that say anything from 1.7 and below is polar covalent. But here's the problem. That's above 1.7. According to that scale, they're saying that this is an ionic bond. Based on our definition of ionic bond, that's not true. So the scale that I would have referenced this to would be a 2.0 scale. So anything 2.0 or below is polar covalent, which this now fits. But I have seen different people in different books use different scales. The book that we actually use is a 1.7 scale. And so, again, this is my lack of knowledge and expertise in the field. So It's in that gray area. 0.3 and less. Sir. Yes. Okay. So it goes from 1.7 down to 0.3. Okay. Well, that was a whole lot on that slide. Negative ions associate with the positive end of the water molecule, which is the hydrogen. We already know that. Okay. Some ionic compounds ionize in solution. Covalent acids form ions in solution with the help of the water molecules. Now, when it says covalent acids, that's your polyatomics, that's your halogenic acids, that's any of your acids. Because what part of the acid, okay, the H plus breaks off? Because you do know that all acids are HX in aqueous, right? Okay. For instance, in hydrogen chloride molecules, which are polar. How do you know that hydrogen chloride molecules are polar? The difference is in electronegativity. So if you want to make that little note there, because they differ in E neg. Those just make sure, if you've never seen me written, that's electronegativity. I'm not writing that big ugly word. Hydrogen is less electronegative than chlorine. So because of that, their difference in polarity creates a polar molecule. Okay? Give up their hydrogens to water, forming the chloride ion, and this new fancy word that I need you guys to know. I know you've seen it, but make sure you circle that word called hydronium. Hydronium. Sure. What hydronium is water that has had a hydrogen ion attach itself to it. Essentially what has happened is, would you all agree that hydrogen has two lone electron pairs? Somehow, some way, what happens is those two electron pairs, just think about this. And I like drawing this stuff so you guys can see it. All right, now, all hydrogens have what in common? One proton. All neutral hydrogens then must have what? One electron. The hydrogen that I have drawn where the little pin is that a neutral hydrogen? No, it is what charged? That means it has done what? Lost an electron. So literally, this H plus is what? One proton. And how many electrons? 0 electrons. I don't care about the neutrons. That means nothing to me. So here's the important point. How many electrons would hydrogen need to become a noble thing? It has how many currently? 0. Who's the closest noble gas? Helium, which has how many? 2. Does water technically have 2 electrons that it could potentially donate to that hydrogen? Yes. So this is what happens. Water actually donates one of its pairs. Not a tetrahedral. No, it's a trigonal pyramidal. Now, if I were to draw this, I need you to think about something else. The water molecule in the reactant form, is it neutral or charged? The water molecule. It's neutral. What have we added to it? We've added one positive thing to it. So do you agree that this whole thing must become positive? Yes. Absorb it. This is the hydronium ion. It is an acid. Yes. When you see this, you recognize it as an acid. Yes, sir. Yes. Interesting. You know more than I do about that. You could, but I've never seen H4O2+. I've never, ever in my life seen it. In theory, It's plausible, but I don't think it's chemically possible. Say that again? Okay. Look it up. Yes. So essentially what happened is this hydrogen right here had no electrons. And it flew around, and let's just pretend that it donated those 2 electrons to it and formed, we'll just call it this bond. Okay? And so this pair of electrons is still hanging out by itself. And the reason it turned positive is because a positive was added to a neutral. Yes, ma'am. Yes. Okay. Any questions here? So again, that's what hydronium is, and that's what it means. Okay. All right. So strong acids. These are your 6. You have 6 strong acids. Now, let me go ahead and show you this. These 3 are all what? Group 17. Now, we talked about this already. There's 2 reasons hydrofluoric acid is not considered strong. Why? We talked about this. The electronegativity makes the molecule too what? Too polar, and then you said the other one. Too small. The atomic radii is way too small. Yeah, that's what I was talking about. Hydrofluoric. No, hydrofluoric. Fluff. Did I? My apologies. Okay. Now, real quick, this right here, I've said this before. What do we call an acid that can donate 2 protons or 2 hydrogens? Very good. Diprotic. Okay. So, you've got to memorize these 6. These are your 6 strong acids. Now, when it says strong, what does it mean to completely ionize? 100%. Okay, 100%. So, sulfuric, nitric, perchloric, hydrobromic, hydrochloric, and hydroiodic. Okay. Oxyacids. What are oxyacids? Amazing how insightful you guys can be. So, acids such as polyatomic acids. And do me a favor, above this slide, write polyatomic acids. That's really what these are. Okay, good. Hopefully you caught all that. So, acids like perchloric and sulfuric, the hydrogen is bound to the oxygen like so. I think there's a picture in here. Is there a picture? Nope. Okay. Gotcha. All right. The pull of the water in the solution is so strong. What do we call the pull of the water? Hydration forces. So let's add that in. Okay. This right here is referring to hydration forces. The pull of the water in the solution is so strong, the hydrogen snaps right off the compound, putting the hydrogen in solution along with the anion of the remaining compound, thus creating an acid. Okay? Go ahead. No. The ions are positive and negative. Yes. Okay? Weak acids such as lactic acid. Where do you get lactic acid? Muscles. That's what you when you cramp, that's what it is, okay? Such as lactic acid, usually ionized less than 5% of the time. Many of these weaker acids are called organic acids and usually contain a carboxyl group. Now, here's the thing about a carboxyl group. AP Bio people, you should know this. A carboxyl group is when a single carbon, okay? So it's one carbon has a double bonded oxygen and a OH group and a bonded, let me get it again, and a bonded. Okay, This is something called a functional group, and there's about 12 of these. Once you get organic chemistry or AP Bio, you have to know these functional groups. Carboxyl is one of them. There's an ester, there's an ether, there's a nitrile, there's a nitride, there's an amide, an amine. Any others? Okay. So, look right here. Do you agree that this carbon has a double bonded oxygen and a hydroxide? That's what it is. So when it says it has a hydrogen that is ionizable, this in this picture right here, what does that tell you about this little hydrogen right here? It's going to snap and fall off. Okay, it's going to snap and fall off. So the carboxyl group does not easily give up its hydrogen. Think about that for a second. It does not give up its hydrogen easily. What would that mean? That means it's going to hold on to it. But what do we have to have for the acid? We have to break it, right? So down there at the bottom, if you want to write makes it weak, underneath where it says does not easily give up, you can write makes it weak. Okay. Right here, that is attached to a larger chain. Yes. Yep. So if you look right here, this right here is that picture. So really, this bond is what you're missing. And it can be a huge chain or it can be really small. But a carboxyl group is that thing attached to something else. No. But the carbon chain can be really, really, really long. One carboxyl group. This right here is this is a hydroxide attached to a carbon, but you have a hydrogen, not a double bonded oxygen. So it's an alcohol. So this is a carboxyl alcohol. If you have a double bonded oxygen and a hydroxide, it's called a carboxyl. There are other ways that oxygen are bonded to the carbon that create different groups. Rarely, but it does. Okay. Yep. So you have things called carboxylic acids. Okay. They're really weak acids, but things like citrus fruit, malic acid, butyric acid, amino acids, nucleic acids, absorbic acid, and acetic acid. So these are different forms. I don't know what you're thinking. Nucleic acid? Nucleic acids are acids? Yes. You've never thought about it, but that's really what they are. So is amino acids. They're acids. Sure, yes. Okay. Now, this is an enormous group. I would never, ever, 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 ever ask you to memorize a group of weak acids. Because here's the good news. If you memorize the 6 strong, what does that automatically make everything else weak? If you can memorize 6, and if it's not in that list of 6, you don't have to think about it. You know what it's automatically. Okay? However, most covalent compounds do not ionize in solution at all. Most covalent compounds, okay? So such as sucrose and ethanol, which is ethyl alcohol, do not ionize. That's why they're non-electrolytes. Yes, ma'am. Okay, we talked about this the other day. The reason hydrofluoric acid is not one of your 6 is because the difference in electronegativity makes the bond between H and F so strong that the hydration forces are too weak to break it. The other one is because the bond is so small, it's hard to break it. Okay? All right. How much time I got? Is that our bill? Okay, then I'm going to stop then.